Welcome. Today we solve longest Subarray with at most k distinct prime factors. Do not worry if you are new. We will go very slowly. The question is, what is the longest contiguous piece of the array whose combined distinct prime factors are at most k? By the end, you will understand primes, unions, sliding windows, and the full code. What are we given? An array nums of positive integers and an integer k. K is the maximum number of distinct prime factors allowed in the union for a subarray. We must return the length of the longest contiguous subarray that satisfies this. If no valid subarray exists, return 0. Remember, a subarray is contiguous. You cannot skip elements. First, what is a prime number? A prime is a natural number greater than 1 with exactly two factors, 1 and itself. Examples: 2, 3, 5, 7, 11. Numbers like 4, 6, 9, and 10 are not prime because they break into smaller factors. Important, 1 is not a prime. Prime factors are the prime building blocks of a number. Look at prime factors of one number. 6 breaks into 2 and 3, so the set is 2 and 3. 10 is 2 and 5. 12 is 2 times 2 times 3, but we only keep distinct primes, so 12 is still 2 and 3. 7 is just 7. 11 is just 11. Duplicates inside one number do not increase the count. For a whole subarray, we take the union of every number's prime set. Example, 6 gives 2 and 3. 10 gives 2 and 5. 12 gives 2 and 3. The union is 2, 3, and 5. Shared primes count only once. The size of this union must be less than or equal to k. That size is the score of the subarray. Example 1 setup, nums equals 7, 6, 10, 12, 11. K equals 3. We want the longest contiguous piece whose prime union size is at most 3. A strong candidate is the middle piece, 6, 10, 12. Let's verify it carefully. Dry run the subarray 6, 10, 12. 6 contributes 2 and 3. 10 contributes 2 and 5. 12 contributes 2 and 3. Union is 2, 3, 5. Size is 3, and 3 is less than or equal to k, so this subarray is valid. Length is 3. Best so far is 3. Why not longer? If we add 7 on the left, we add prime 7, and the union becomes size 4, which is bigger than k. If we add 11 on the right, we add prime 11, and again, size becomes 4. So no length 4 subarray works here. The answer for example 1 is 3. Example 2. Nums equals 4, 6, 9, 18, and k equals 4. 4 gives 2. 6 gives 2 and 3. 9 gives 3. 18 gives 2 and 3. The whole array union is just 2 and 3. Size 2 is less than or equal to 4, so the entire array is valid. Answer is 4. Example 3. Nums equals 6, 10, 15, and k equals 2. Any pair of length, 2 unions to 2, 3, and 5, which has size 3, too big. But each single number has exactly 2 distinct primes, which is allowed. So the longest valid length is 1. Answer is 1. Why sliding window? The array length can be 100,000, so checking every subarray is too slow. Important property: when you grow a window to the right, the union of primes never gets smaller. It only stays the same or grows. That monotonic behavior lets us use 2 pointers, expand right and shrink left when we have too many distinct primes. Picture the window. Keep 2 indexes, left and right. The window is nums from left to right. Maintain a frequency map of primes currently inside the window. Distinct primes means how many primes have count greater than 0. Whenever distinct becomes greater than k, move left forward and decrease counts until the window is valid again. We need fast factorization because values go up to 100,000. Use a smallest prime factor sieve, often called SPF. Pre-compute an array where index x stores the smallest prime that divides x. Example, SPF of 12 is 2, of 15 is 3, of 49 is 7. Build this once, then factor any number quickly. How to factorize with SPF? Take 60. Divide by 2 to get 30. Divide by 2 to get 15. Divide by 3 to get 5. Divide by 5 to get 1. Distinct primes are 2, 3, and 5. Always divide the current value by SPF of the current value and store primes in a set so duplicates are ignored. Window dry run on 7, 6, 10, 12, 11 with k equals 3. Add 7, primes set size 1. Add 6, add 2 and 3, size becomes 3, still valid, length 2. Add 10, add 5, size becomes 4, which is greater than k. Now we must shrink from the left. Continue. Remove 7 by moving left. Window becomes 6 and 10 with primes 2, 3, 5, size 3. Add 12, no new primes, still size 3, length 3, update best to 3. Add 11, size becomes 4, so shrink again until valid. Final best length stays 3, matching the official answer. Why a frequency map, not only a set? Because two numbers can share the same prime. If both 6 and 12 contribute 2, removing only one number must not delete 2 from the window. So keep a counter. Each prime maps to how many times it currently appears. When a count drops to 0, distinct decreases by 1. Add on expand, subtract on shrink. Algorithm steps. 1. Build the SPF sieve up to 100,000. 2. Pre-compute the distinct prime set for every element. 3. Start left at 0, best at 0, empty counter. 4. For each right, add that element's primes. 5. While distinct is greater than k, remove the left element's primes and move left. 6. Update best with the current window length. 7. Return best. Here is the helper code. Build SPF initializes every index to itself, then marks multiples with their smallest prime. The factors function repeatedly adds SPF of x and divides x by that prime until x becomes 1. These helpers let us factor every array value efficiently before the window loop. Here is the sliding window code. Pre-compute prime sets for all numbers. Use a counter and a distinct variable. Expand right by adding primes and increasing distinct when a count goes from 0 to 1. While distinct is greater than k, remove primes of the left element and move left. After fixing the window, update best. For 7, 6, 10, 12, 11 with k3, this returns 3. Code walkthrough in plain words. First, prepare fast factorization. Then, for every right endpoint, expand the window. If too many distinct primes appear, shrink from the left until the window is legal again. Every time the window is valid, record its length. Because every right endpoint keeps a valid window, we never miss the longest answer. Edge cases for beginners. If a single number alone has more than k distinct primes, that element can never be included. If every element fails, return 0. If k is very large, the answer can be the full array length. If many numbers share primes, the window can grow very long. And because values reach 100,000, the SPF preprocess is important for speed. Key takeaways. Prime factors are the prime building blocks of a number. A subarray score is the size of the union of those primes. We want the longest subarray with union size at most k. Growing a window never removes primes, so sliding window works. Use an SPF sieve for fast factorization. Keep a frequency map of primes. Expand right, shrink left when distinct is too big, and track the maximum valid length. That is longest Subarray width at most k distinct prime factors, explained from 0.